This question is about catalysis. Zeolites are used as heterogeneous catalysts in the catalytic cracking of alkanes. Tetradecane, C14H30, can be cracked to form octane, so oct meaning 8, ANE meaning alkane, 2N plus 2, so 18, and a cyclic alkane. Now they're CnH2n, they're isomers of alkenes, so they have 2 less hydrogens to join them into the ring. Give an equation for this reaction. So C14H30 is cracked, and so we're breaking it down into C8H18. Now there's probably more than one right answer here, but I'm going to go for the simplest. If you subtract 8 from 14, you're left with 6. And hopefully, if this has worked, we will have 12 hydrogens. And we can just double back check. 18 add 12 is 30. And that is our answer. So state the meaning of the term heterogeneous. That is when the catalyst, the catalyst is in the same, it's not in the same, it's heterogeneous, is in a different state or phase to the reactants. A student determines the concentration of ethane dioate ions, which are here, in acidified solution by titration with manganate, which is here. The reaction is warmed before the addition of the potassium manganate 7 because the reaction is slow at first. When more potassium manganate 7 solution is added, the mixture goes colourless quickly due to the presence of an autocatalyst. Explain the meaning of the term autocatalyst. So an autocatalyst is when the product of the reaction catalyzes the reaction Explain using equations where appropriate why the reaction is slow at first and then goes quickly. Well, so it's slow at first. If we look back at what we underlined about who was reacting, as 2 negative ions, you see that they're the 2 things that are reacting, would repel. So EA activation energy would be high as energy needed to overcome the repulsion. And then it says why it's slow and then goes quickly. So once some, and we have to look at the products to see who's our autocatalyst. It's this Mn2 plus. Once some Mn2 plus forms, it acts as a catalyst. Oppositely charged ions attract. So EA is lowered. Acts as a catalyst, it provides an alternate route of lower activation energy. We now need to come up with the equations for the catalysis. It's a bit tricky. We have been given the overall equation. So what's helpful to do is to think about the overall equation, MnO4 minus, and split it up into some half equations. MnO4 minus is going to Mn2 plus. I'm just going to balance that half equation using the rules. Okay, and our other half equation, C2O42 minus, is going to CO2. So I'm going to balance that equation. Now the top equation that we've written is a reduction and the bottom one is an oxidation. Now our catalyst is Mn2+, and it's going to catalyse the reaction because it can convert itself to Mn3+, and then Mn3+ can go back to Mn2+. Now for Mn2+ to go to Mn3+, it would have to undergo oxidation, and so I'm going to be able to combine it with the reduction half equation. So Mn2+ is going to go to Mn3+ plus an electron. Now to combine these two, I'm going to have to multiply by 5, and then I'm going to combine, and I will notice that there are 5 Mn2+s in the bottom equation and 1 in the top, so I'm going to cancel out one of them and make this 4, and then combine them. So the equation I'm looking for is MnO4- plus 8H plus 4 Mn2 goes to 5 Mn3 plus 4 H2Os. And the top bit is my working. I'm just going to bracket round that. And this bit is my equation, so I'm just going to make that stand out. Then we've turned the Mn2+ into Mn3+, so it's going to react with the other half equation. It's going to reduce back to Mn2+. I'm going to have to balance the charges by doubling up, and again I'm going to combine that and cross out the electrons, and I'm going to get C2O4 2- plus 2 Mn3 plus goes to 2 CO2 and 2 Mn2 plus. And put a little box around that and bracket my working. And then I've shown using equations how Mn2 plus is the autocatalyst. The reaction between peroxydisulfate ions and iodide ions in aqueous solution can be catalysed by cobalt 2+. So let's just have a look at that. So cobalt 2+ here is over here, which means it's on the right hand side of one of these potentials in the electrochemical series. Makes it a reducing agent. So it's going to reduce whoever is needing to be reduced. If we look, our reagents are I- and S2O2-. The peroxydisulfate is the thing that needs to be reduced. Suggest how cobalt 2+ catalyses this reaction. So cobalt 2+ is on the right hand side. It's going to react with something on the left hand side. And that is because the standard electrode potential for peroxydisulfate turning into sulfate is greater than the electrode potential for cobalt 3+ to turn into cobalt 2+. What that means is that the first thing on the left-hand side can react with the last thing on the right-hand side. So cobalt 2+ is a reducing agent. It's on the right-hand side. Reduces S2O8 2- to SO4 2-. It causes that reaction to go forwards. It itself is oxidized to CO3+. So this goes forward and this one goes backwards. Then what happens is we've now got cobalt 3+, and the standard electrode potential of cobalt 3+ to 2+ is greater than that of iodine to iodide. Cobalt 3+ is now on the left. Cobalt 3+ oxidizes, things on the left are oxidizing agents, oxidizes I-, the thing on the right, to I2, and is reduced back to cobalt 2+. We've regenerated our catalyst.